Hello, hello, good afternoon, people. My name is Aaryan Dubey, and I'm going to present the research paper on encoding human behavior in information design through deep learning. So, what is this paper is all about, right? It's simple. First, you need to understand few things, like what is information design, right? It's simple. A sender aims to pursue the receiver to take a certain actions. So let's just see. When you open Instagram or Facebook, right, you get some targeted ads, right? So you are a receiver to those ads, and a particular sender, Google ads, Facebook ads, are the sender, and they are sending those information to you to take a particular action. So as a receiver, what you're going to do is that if you see some, okay, you need to buy some Xbox, you're getting some Xbox ads, right? So you're going to go and buy. So that is an information design type of thing, right? A sender aims to pursue the receiver to take a certain action by strategically revealing information. Receiver might exhibit different behavior, right? So you are a receiver, you can exhibit the very different behavior, right? So one is like Bayesian rational assumption, right? They say that they have prior beliefs, right? So you have prior beliefs, okay, should I buy this? Should I not buy this, right? So this is a prior belief. And that belief gets updated with the receiver info. So you already know, okay, I shouldn't buy this. But then you get a receiver info through ads or anything else. You think, okay, now my belief is getting changed. This has some use, this is not some use, right? So yeah, generally that. And this probability of the updated probability before the prior probability is 50%, then becomes 60%. This updated probability is called posture probability, is the updated belief. That is, your belief has been updated, right? So a rational person will follow this Bayesian belief. But are we rational? That is the question, right? Because we don't follow that perfect scenario every time, right? Bayesian assumption says that, okay, you're getting good things here, you will always go and follow this thing. But I don't think so. Humans are based on that scenario. So that is the particular paper, right? They say that we initiate study of behavior information design through deep learning. They say that a sender aims to pursue the receiver to take certain action by strategically revealing certain information. They say that exhibit different behavior pattern other than standard behavior rational assumption, as I said to you guys, right? We generally are not the perfect human beings who's going to say, okay, it's like buying a gaming console, okay, it's going to be bad, but no, why shouldn't I? We should buy it, right? We are going to spend money, something like that. So they propose HAIDNet, a neural network-based optimization framework for information design that can adapt multiple representation of human behavior. So they are saying that they're going to encode human behavior in neural networks, which if you go deeper into the paper, it's not very clear how they are doing that. They just train two neural networks and they say, okay, yeah, this is the encoding. But yeah, let's see further down the paper how things will pan out, right? So they say that through extensive simulation, we show that HAIDNet can not only recover information policy. Information policy is generally what information design is made through, right? You have an information policy, then you're going to make an information design. So if you are Google Ads or you're using Google Ads, right? So you are a sender, you're going to make an information policy, and then you're going to design that policy. Okay, this is the information that we need to send. So this is generally the information policy. So they say that information policy that are near optimal compared with known analytical solution. Known analytical solution is generally Bayesian assumption, other things, right? But they can also extend to designing information policy for settings that are computationally challenging. Like there are multiple receivers. Generally, in real world, there are always multiple receivers. Or for settings where there are no known solution, where receiver behavior does not follow Bayesian rational assumption. That means the receiver is not perfect in his decision, right? He will say, okay, yeah, I shouldn't buy it. Even if it's bad for me, I should go for it or not, something like that. That's the Bayesian, that's the opposite of Bayesian rational assumption, right? So they say that they also conduct real world human subject experiment and demonstrate that our favor can capture human behavior from data and lead to more efficient information policy for real world receiver, etc. Right? So introduction to the paper. What's the problem? A player with an information advantage, right? The sender, it can reveal info to another player, that is a receiver, right? We have a sender, we have a receiver. Why does a sender wants to reveal information? To take some action. Example could be shops, politics, etc. Great example will be politics, right? A politician will reveal some information to get some votes, right? Even that particular information is good or bad, right? For sender, it will be like, okay, we should take the vaccine or not. Some politician will say, okay, vaccine has bad effect, and it's going to influence the prior belief of a particular set of population. Even if they are going to take the vaccination, they will move back from that particular belief. Okay, vaccination is bad, some politician has said, and they're going to take votes from it. So that's the particular thing, how they influence people. Like this is the example of politics, right? Literature and information design was known as Bayesian persuasion. Simple. How you persuade using Bayesian method. Bayesian method is generally a perfect scenario where a receiver is influenced by sender, and receiver is going to take an action that is going to benefit him, even when the sender reveals the information and receiver knows, okay, this information that sender has revealed is bad for me, but I as a receiver is going to take a certain action that is going to benefit me, not the sender, right? So it's good, but there's always a but, right? Assume receiver is Bayesian rational. They say that it's only good if receiver is Bayesian rational. Perfect, right? What I explained to you. Characterization, the optimal information policy remains not racially reflected, as they say. Info policy is nothing, it's just what sender sends the receiver, right? Simple and easy. So yeah, they generally explain these things in these paragraphs. They say that while Bayesian persuasion offers an elegant framework for formulating the information design problem, right? But it has two limitations. First, receiver is assumed to be Bayesian rational. This means a posture in Bayesian manner choose the action that maximizes the expected utility, right? Simple. After that, they say that it has suboptimal outcomes. In this wide range of human behavior expressed either as traditional analytic flows from behavioral models or as data-driven model, is design and information policies with respect to provided human behavior. Second, what they say is that despite the decades of efforts characterization, the optimal information policy remain notoriously difficult, right? They say that two authors here shows that it is pretty hard to compute optimal expected sender utility. Sender utility is generally what information policy you guys are sending to the people, something like that. Sender utility is simple, like I am Amazon and I'm sending an ad to a particular customer through Facebook ads, through Google ads. So that is a sender utility in this case. Those ads are sender utility. And in multi-receiver setting, where each receiver only has binary actions, PR to even approximate this optimal sender utility with any constant multimeter fact. It's generally saying that there's no optical analytic solution to finding that optimal information procedure. So finally, in this work, what they say is that they initiate a study of automated information design, right? That encodes human behavior into a design process, right? How it's different. They say that they adjust to multiple representation of human behavior pattern, right? And they also encode human behavior into design process inspired by different methods, HAIDNet, deep learning for information design. Generally, that's the particular name as specified here. We propose HAIDNet, an optimization framework that leverages neural network architectures to information design. Unlike existing words that assume rational human behavior, as is explained, Bayesian rational behavior, right? So this is the rational human being behavior. Our optimization framework can adjust to multiple representation of human behavior patterns, including standard behavior model, representative analytic from data-driven model trained using machine learning approaches. More specifically, they say that they encode receiver behavior as a function and represent the loss in optimization framework as a function of receiver response. And I think this loss function is very interesting how they are going to encode it here. But as much as it is interesting, it's as much as it's a little bit weird to discuss. Yeah, let's see how it goes. So they just explain their contribution to the paper. They say that study of the automated information design, that's called human behavior. Now we have the reveal. What is HAIDNet, right? Human behavior encode neural network mechanism for automated information design, namely HAIDNet. It enables us to optimize senders information policy based on given human behavior. They say that we incorporate neural network architecture for information design problems. Generally, you will see a lot of this thing repeated in the whole paper. Generally, we need to understand neural network architecture that's going to form information design problem. And it's not really neural network is needed for us. They just used it here, as we will see. So they also say that we evaluate our approach using extensive simulation in simpler setting with no analytical solution. They say that we had HAIDNet can recover optimal information policies. Yeah, of course, that's the whole paper right now. And after that, they show that they use real human with subject experiment. I think that's the most interesting part of the paper, and demonstrate that our framework can adapt to scenarios we do not have access to human models of priority. They say that our approach can learn human descriptor and from behavioral data, incorporate into optimization framework. and result in simple, effective information policy design, as they say. Now we have like related works, similar. Like I'm going to explain very short. Their works differ because they have incorporated human behavior. Their information formulation, our information for formation design, what they say, is built on seminal work on Bayesian persuasion. Their work extends on previous research by designing a framework that can accommodate both analytical form and data-driven form of behavior. Why this analytical form of behavior? Because, yeah, let's see. Because, see, there's a concept known as human descriptor that we'll see in downwards paper, right? Let's see more. So let's see. Bayesian persuasion basics. Right? What is Bayesian persuasion? I'm going to explain it in a little bit short nature. Then we'll go to this whole numerical approach of the whole method, right? So Bayesian persuasion. Suppose one person calls him a sender, wishes to persuade another, call her a receiver to change her action, right? Simple, as I explained in the above examples. So if receiver is rational based, right? If the receiver is rational Bayesian, it can sender persuade her to take an action he would prefer over the actions she was originally going to take. If receiver understand that sender chooses what information to convey with the intent of manipulating her action for his own benefit. So, can sender still gain from the persuasion? If so, what is the optimal way to persuade? So, as I said, there are three players. Sender, the one who's sending the information policy or trying to persuade the receiver, right? Receiver, it takes action based on the state of nature. So, what is state of nature? It could be like anything. It's generally a state, I would say. Like if a farmer is planting a crop, right? So for him, state of nature could be we should plant the crop or we shouldn't plant the crop, something like that, right? So yeah, state of nature. Sunny weather is more common than rainy weather, so assign a higher probability state 1 and state 2. Yeah, I said it a little differently, but yeah. State of nature could be sunny weather or common than rainy weather, so assign a higher probability state 1 to sunny weather. Oh, come on. And state 2 to the rainy weather, right? If receiver is a farmer, the action might include planting the crop, irrigating the field, and wait to see if it will rain, right? Simple. Now, depending on what action the receiver will take and what actually happens, that means the state of nature. So that means if receiver is planting the crop and it rains, right? Everything will be destroyed. Receiver gets some type of payoff or utility. In this case, like if he plants and it rains, right? The payoff utility is minus because everything is destroyed. Nothing gets saved, right? So this payoff could represent anything from profit for the farmer to happiness for an individual. So if farmer plants crop and it's sunny, they might get a high payoff. But if it rains heavily, they might get a low payoff. So here where the sender comes in. Sender also cares about what action the receiver takes and what actually happens. So the sender utility or payoff is also affected by these factors. For example, if sender is a government trying to stabilize the economy, they might want farmer to plant crops regardless of the weather, right? So the utility could be higher if the farmer takes an action, even if it's risky. So government say, okay, plant the crop. What will happen? Rain. There's some probability to rain, but they will generally, okay, we don't care if you out of 10 or 20 farmers, they're trying to, influence. 10 farmers plant the crop, they will be good for the economy, they will save, but other 10 farmers will get destroyed or something like that. So that's the government intention right now. So sender intention is to get profit for his benefits by sending information to the receiver. But receiver should be Bayesian perfect, right? So not take that particular action. So in summary, you have different possibilities of what can happen. That is the state of nature. A belief about how likely each probability is, that is the prior distribution. Actions that the receiver can take in response and payoff or utilities for both receiver and the sender based on the action taken and what actually happens. So what is a signal space? As you see in the numerical, I'll explain it. Signal space is all the action that a sender can take. Conditional probability is probability based on action and the state of nature. So generally state of nature is, yeah, okay, it's sunny and action taken is plant the crop, right? So utility would be good. So that is a conditional probability. If it is sunny and farmers can plant a crop, so that will be a probability of that. That's generally basic of Bayesian persuasion in, I will say, theory terms. Now let's see in numerical terms, right? The sender goal is to design an information disclosure policy that pursues the receiver to take certain actions to maximize the sender objective, right? So let's just see. We have state of nature theta, as I explained. What is state of nature? There it is. Come on. Yeah. State of nature. Sunny weather, more common, rainy weather, not that common state 1, state 2. So this could be a state of nature from an infinite set 1 to m according to a prior distribution, right? The prior is a common knowledge to both sender and the receiver. Receiver utility, this particular utility, that is action based on this particular state of nature, depends on the receiver action, that is belong to an action set. Theta and state. The sender utility also depends on the receiver action and the state. So what receiver is going to take action on that particular state, use sender utility also based on that. So as you guys recall, receiver utility, sender utility generally is designed to maximize the profit or a particular positive function for both sender or the receiver, right? They're not interrelated, but they're kind of interrelated, right? A sender can observe the realized state while the receiver cannot. The sender can utilize this information advantage to pursue the receiver to take the desired action. In particular, before observing the realized state, sender can commit to an information policy. So now we have information policy pi, right? Specifying what signal to present to the receiver condition on the realized state. So they know, like, okay, it can rain, so we should plant crop, we should send signal to plant crop, etc. Right? So more formally, an information policy pi consists of a signal space. Signal space could be anything, right? If a weather forecast want to send a particular signal to the farmer, okay, plant the crop, something like that. So signal space is based on that. Set of conditional probabilities where, yeah, these are all the methods that define information, etc. There's the probability to send signal to the from this particular set of signal space, right? Crop, plant the crop, don't plant the crop, whether it's rainy, whether it's sunny, something like that. It could be anything, right? This information disclosure policy is known to the receiver and specify how the sender discloses information to the receiver. Where state theta belong to this particular, right? Sender sends information according to the policy. Yeah, it's generally that only. I'm gonna go to the example, right? So consider a scenario where an online retailer, the sender, aims to pursue the buyer, the receiver, to make a purchase, right? The retailer products are directly coming from factory, and the product quality, represented by binary state theta, yeah, is drawn from prior distribution. The buyer's utility, that is this particular utility, that is, this is the action, this is state of nature, depends on both binary purchase decision A and the binary product quality theta. While the retailer's utility is the state dependent and only depends on the buyer's purchase decision. So for example, goal of the retailer is to pursue buyer to make a purchase, right? So if this particular utility action is 1, so he has to take an action 1 for this. The buyer only wants to purchase when the product is good. That means action should be 1, and this particular theta is related to action. Yeah, it's simple, right? If the product is good, they will buy. If product is not good, they will not buy. Action would be 1 if product is good, and the probability of the state of nature should be 1, right? So what they do is that in order to pursue the buyer to purchase, retailer can commit to performing noisy product inspection. So this is a particular function that is going to imply to reveal information. This is generally known as the information policy. Spoiler alert, to reveal information about the product quality. For example, the inspection might signal the product quality to satisfactory 80% chance, right? If the quality of product is indeed satisfactory, that means state of nature is 1, and this particular conditional probability, I forgot what this is. So this, I think it's the state of nature, what the particular action a particular sender sends. So if this is 1 and product quality is 1, that is good. So it's 80%. Signal the product quality is unsatisfactory with 90% chance. If the quality is indeed unsatisfactory, that means it should send 0 and product quality is also 0. So it's 90% chance of it. This is an information policy. The information design problem is for the retailer to identify inspection policy that maximizes the probability of selling the product to the buyer, right? In simple words, a sender, right, online retailer has to design an information policy that can influence the receiver to see, okay, the product is satisfactory, you can buy, even if the product is unsatisfactory. You will see, like, spoiler alerts, in this whole algorithm, what they try to do is that they are going to maximize it only the online retailers' profit or something like that. In this scenario, whenever the online retailers get the perfect information policy, there's always a huge loss for the receiver, even if it's successful or something like that. So its whole algorithm is designed like that. So I will take this algorithm with a grain of salt. But yeah, even if you want, we can go with this approach in a little gray way. But yeah, let's see. We'll discuss it further, right? Yeah, main algorithm. What's the main algorithm? Is HAIDNet, encoding human behavior and automated information design. So I generally describe how we modelize human behavior in information design. This is the particular algorithm. So I'm going to explain it a little bit here. So this is the sender utility. This is the receiver utility. This is the particular action based on a particular state. This is the prior distribution. Like what's the prior assumption? Like, okay, if it's rain, the prior distribution, okay, it will rain, it will not rain, or something like that. It could be anything. So prior distribution is the probability that has already been assumed. Receiver utility is a particular function. It's a state of nature based action. So what action will be taken on if the state of nature is theta 1, 90% probability, 10% probability, something like that. So this is our receiver utility. Same with sender utility. What they tend to do is that they take these three, put it into a neural net. A three connected layers, they don't define what's the neuron here, they only define, oh, we use ReLU activation function here. Other than that, nothing. What the end layer activation function is ReLU, I don't know. They never defined it here. They just they say that, okay, we're going to take these three, pull it into neural networks. It will print an information policy, right? Information policy, what action should you take on the state of nature? So it should utilize the increase our what do you say, profits, right? That would be the best answer here. Then information policies pass through a human descriptor. I'll explain what this human descriptor is, right? Simple. Human descriptor is also neural net. Spoiler alert again. So they say that human descriptor is also neural net, and this neural net predicts receiver behavior. Then what they do is that they take the sender utility, receiver behavior, and information policy, and design a loss function here. Loss function is information policy into receiver behavior into sender utility and a negative sign here. So they create a loss function here that's going to compute. But they never defined it here like, okay, you're going to optimize this loss function, you're going to optimize sender optimization function, right? It's a neural net, fully connected neural net, right? Simple and easy. But how are you going to optimize human descriptor? Is this loss function is used here to optimize human descriptor? They never defined it anywhere. So I'm still confused how we can optimize it. Maybe you use this loss function to optimize both this and this, and in the end, we'll have an algorithm. But yeah, that's the basic algorithm right now. I'll explain it here. So they that encoding human behavior. So to test it, right, if this algorithm works or not, they replace human descriptor. Human descriptor with neural network is their algorithm, right? They sometimes they replace human descriptor with Bayesian persuasion, and there's another algorithm known as TH algorithm that we'll see. So they compare with this human descriptor with Bayesian persuasion and then the TH algorithm. So encoding human behavior. Bayesian persuasion assume that receiver is Bayesian, rational. That means he's perfect. However, in practice, in this assumption does not hold, as we know. Receiver may exhibit systematic bias both in belief updating and decision making. You might be thinking, like, what is this belief updating? Belief updating is updating this priority distribution, right? You will update, okay, yeah, I get some sender utility, I get some information, I should update my belief. That prior belief doesn't make sense, right? So in the following discussion, they formulate a sender problem on finding the optimal information policy. Human behavior descriptor, this particular function. What they do is that for any receiver utility, that is this particular receiver utility, and a prior information, that is prior distribution, sender information policy, that is the sender information policy that we get, and a signal space this, and human behavior descriptor is denoted by a particular this formula, representing the probability for a human receiver to choose a particular action A belonging to capital A is set, right? While seeing the realized signal, this particular. Yeah, generally this, right? What state of action should you what state was the probability of taking this particular action from the state of theta 1, something like that. So in context, they generally just put human descriptor value as this. Now, below the few example of human behavior descriptor. Then they did take Bayesian rational, generally like it will take the perfect Bayesian formula. Generally, I was trying to decrypt it, how they use Bayesian rational formula. So they use the Bayes formula, but yeah, it doesn't make sense when you like try to compute anything with it. So yeah, I skipped this method. Then we have th model. Yeah, I didn't deep dive into this method right now because yeah, generally didn't seem that interesting to me for now. Then I went for this data driven human descriptor. So they generally define this particular whole this algorithm. Now this whole algorithm as this human descriptor. What particular action should a sender takes based on a particular action to represent human behavior. Suppose we have action to sufficient human behavioral data. Instead of expressing, we use a closed form analytical expression. We train a machine learning model to approximate this function and utilize the learned model as a human behavior descriptor. As I told you guys, this human descriptor can be converted to a machine learning or deep learning model for a data-driven approach. So HAIDNet framework, right? As presented in figure 1, HAIDNet consists of two modules, sender optimization module, human descriptor. Sender optimization module is the neural network responsible for optimizing the sender optimal information policy. Yeah, it's generally what I explained that. So they use three descriptor. I'm going to be quick, right? Human descriptor is 3 Bayesian, probability weighing discrete choice, TH model, then data-driven human descriptor. And then just they defined it here. And yeah, this is the loss function they are computing. So yeah, loss function is simply this: priority distribution, information policy, and the human descriptor function. They're going to take the multiplication of that, and then there's going to put -1 here. This is the real loss function. Generally, the optimization process is defined like that. So there is how there is one thing more, that if the loss function, how you're going to optimize loss function if human descriptor is Bayesian, right? So they define it too, like how they solve this particular model. The human descriptor can either be model-based, or Bayesian rational, or TH model. So they define it here. This model requires many cases, neural net. However, in Bayesian rational models, since receiver chooses the action that maximizes its expected utility, this argmax operation take the human model not differentiable, right? To overcome this issue, we approximate Bayesian rational model using softmax method instead of argmax with sufficiently large scale softmax scale parameter. More concretely, let UA be the expected utility for action A, then softmax operator, yeah, then define this function to use. I didn't deep dive into it, how we can use for the Bayesian. I deep dive into this. I think I have a formula that, not even a formula code that I think works. And after that, how the optimization implementation happens is generally they optimize HAIDNet, train neural network on 3 fully connected layers, employing ReLU activation function, Adam optimization, adder optimizer, very simple neural networks in my opinion. Model is trained on 100 batches of size 1024, then a total of 102K 400 uniformly drawn instance problems, something like that. So after that, simulation, right? I'm going to skip these things. I think I'll just come back to setting with efficient solutions, setting with known solutions. Generally simple. I'll come back to this, like real world human subject experiment. I think that's the most interesting experiment right now. But yeah, if you guys want to deep dive into this, it's generally explaining, right, how if the solution is not known, how it's going to perform. And yes, spoiler alert, their algorithm is good in these cases. So yeah, I'm going to skip it here and go into this, like human descriptor analysis. I think that's good. So they say that in human subject experiment, they present a product purchasing example in section 2 to human participants. Where are you? Human subject persuasion. This example, what I explained to you guys, like online retailer, there's a probability of getting, okay, what's the probability of if the product is good or product is bad, right? So they explain that to the particular participants in the cases. There are many participants we'll see afterwards. So in human experiments, we present product purchasing example to human participants. Each human participant is asked to make multiple rounds of purchase decisions. Right? In each round, participant is presented a product with unknown binary quality, good or bad. Participant is told that a noise inspection has been performed on the product and given the conditional distribution associated with the inspection. That is probability to receive a good or bad signal given the product is good or bad, right? Finally, the participant is given realization of the inspection signal and asked to make the binary decision to purchase or not. That means, as much as I understood from this, is that they have been given a probability, okay, this product is good, this product is bad. The participants' payments depend on their purchasing decision and true product quality. Task inference is included in Appendix C. Yeah, we'll see after that. Spoiler alert. Text accuracy to different human behavior descriptor and human subject experiment. So they did that experiment, right? So they used three descriptors: Bayesian rational, TH model, and neural network, right? And you can see the accuracy: 56%, 73%, and neural network 77%. So experiment procedure is that we have recruited 300 workers from Amazon mechanical truck. We set the base payment of $0.50. They can earn additional bonuses. Average hourly rate was 11.60. Yeah, simple things, right? Learn human behavior descriptor. Goal of the first phase experiment is whether we could learn accurate human behavior descriptor from worker response data. So in this phase, they recruited 100 workers. Each worker completed 20 rounds of purchase decision. Parameters for each decision is prior, sending utility, receiver utility, and policy, right? We already know what receiver utility is, sender utility is, prior function is, and the policy was drawn uniformly at random. We splitted the collected data into training set, test set, with 80% of training, 80% of data for training, and 20% for testing. So after that, the trainer examined the performance of three behavior descriptors as defined here: Bayesian, TH, and neural network. This descriptor makes standard assumption that human are Bayesian rational. There's no training needed for this descriptor. Yeah, simple, makes sense, right? There is no training needed for this descriptor. TH model, they fit the parameters of TH model from data to minimize the least square error. Neural net, three fully collected layers to fit the data into training set. They further split the training set and use 25% of data. Yeah. So yeah, after that, they evaluate the health HAIDNet. Yeah, then examine how accurate is descriptor predict human behavior. It's reported in table 4, which is generally as I showed you guys here. Right. After that, in the second phase, they recruited again 200 workers to examine the performance of different information policies. In particular, we examined the following 4 information policy. This information policy is drawn from digit distribution, a random information policy, then Bayesian rational information policy, TH policy, and a HAIDNet policy that generally like did it, right. So they say that sender utility is the highest is around HAIDNet, as shown in this particular graph. So yeah, they generally defined it how it's done. Like they randomly assign one of these 4 policy treatment, then they presented 20 rounds of purchase decision coupled with associated information policy in the treatment. We measure the average sender utility in each treatment. Result is shown in figure 4. As much as I've seen, I haven't seen sender utility defined anywhere for this, or I don't know. So in addition to examine sender utility, we also, this is very interesting. We also measure receiver utility in each treatment. See the full information in Appendix C. Let's see. Yeah, comparing sender and receiver utility of different policy in humans experiment. So at random, sender utility is less, receiver utility is very good. Bayesian rational policy, it's balanced, I would say. Like still receiver utility is very good. TH policy, receiver utility decrease. Sender utility increase. HAIDNet, 66%, 53 2%. Receiver utility decreased as much as sender utility is increasing. Yeah, helps to find a policy that leads the higher sender utility. It comes at a cost of reducing the receiver utility. That's an interesting case. But yeah, it could be a very interesting case if we put it in fraud detection, right? Receivers could be of fraudsters, and then we can, reduce there as much as the utility. I was thinking in that context. But yeah, let's go back to our case study that we were doing. These are all the references, as you guys already know. But yeah, we observe the policy HAIDNet leads to an average receiver utility of 0.532, which is the lowest of the 4 treatment. This creates a concern, right? That when we incorporate the knowledge of receiver behavior to optimize the sender utility in information design, we are potentially exploiting the knowledge of receiver behavior and hurting the receiver. We offer more discussion in the discussion section of the paper, right? Then just generally define generalization and limitation. Yeah, there are a hell lot of limitations for this method. I'll skip this. I'll go to negative impact and social impact. Finally, we highlight the potential negative social implication of the use of information design frameworks. Senders often represent party in power, while the receiver is less advantaged position due to asymmetry of information access. While it is possible to use information design for social good, I don't think so they can use it. Guiding the receiver towards action that is beneficial for himself or public. Yeah, this is generally not possible, right? I don't know if you guys have seen Westworld or not. This is generally defined that, like, use information design policy for social good. They didn't. I think the Westworld is the best example for this. Should you use information design for social good? And what is social good? Like everyone Receiver towards action that benefits for himself or the public or society. That's the question. The vast majority of information design literature, including our one, focus on optimizing sender utility. When the interest of sender receiver not aligned, optimizing the sender utility could result in negative impact of the receiver. But yeah, that's the basics of the paper. I think uh, I coded it out this whole scenario. It may be interesting to see. But yeah, it's a very simple one. So I did as like a sender optimization function, right? Per simple neural net, right? So this is the three fully connected layers, but I added this layer, input layer and output layer. I don't know if it's generally the particular layer or not. I just added it. Like so, the a fully connected layer, four linear layer that are fully connected to each other, right? This is the output layer, FC3, FC0 is our input layer. Then we have a forward layer with ReLU activation function. Yeah, I write it here like ReLU or something else. That is the question. Should we use ReLU in the end? I use softmax in the end. Yeah, let's go forward towards it. Then I defined a human descriptor. I don't know if it could be a machine learning algorithm, but yeah, I already define fully connected two layers again. Like one should take the input, other should take the output, then ReLU activation function, then just print the output layer. Then I decide a receiver utility function, generally like this. What they define it here is 1, 0, 0.1. I just put 0, 1, 0, 1, 0. This is a receiver utility. Then a priority distribution, 0.7, 0.2. I needed it for the shape, so I just put it there again. Then we have sender utility function, that is 0.9, 0.1, 0.2, 0.8. Yeah, just to see how the algorithm works, right? So yeah, as usual, receiver utility, prior distribution, sender utility. Now the loss, right? Loss will do an interesting thing. So let's take the model output, what our the sender optimization module gives, right? Into sender utility, that is this particular function, into prior distribution, as much as they were saying. Or I did something wrong here. But yeah, sorry, receiver behavior. Yeah, we'll see how this pans out. I think I explained it wrong here. So yeah, I put the input data, that is I can concatenate these whole one, and we have input data or something like this, 2x6 matrix. I don't know if it's correct or not, but then generally, yeah, just design the layer. I took the output, I took the softmax function. We'll have output of something like this. This output is generally information policy here, right? It's 80% one, 30%, but yeah, I have something like this. And then we take the information policy as human input. That means, as you see, this information policy goes into human descriptor, right? So simple. I was going to put it in the human descriptor. Hidden layer is 32. Output is 2. Yeah, simple neural network stuff. Then we get RB. It's not Red Bull, guys. It's the receiver behavior. So we have RB here. Then we define loss again, just to see. So loss take model output. That is our information policy that comes from here. Then RB is generally the receiver behavior that we get from human descriptor module. And then the prior distribution that we defined earlier, that is here, right? These are the things that generally gives us loss, right? Then I run an experiment just to see how things will work. There are two things, right? One is I did an optimizer test that has both of these parameters just to see how things will pan out. And then we have optimizer for only models. Yeah, then the simple what I did earlier, I did it in a loop or epochs, etc. I did the loss callback or something like that. Loss is calculated using that only. So simple, it's like this only. Model takes the input data, it gets the output. Output gets converted to information policy. Information policies go to human descriptor. Human descriptor gives receiver behavior. Receiver behavior goes into loss. Loss is calculated. Took the sum here, and then we just optimize the whole scenario. And we'll have, yeah, this is for, I think, optimizer test step. It's committed out right now. But loss is decreasing kind of because it's negative utility here. So yeah, that's it. That's it. Thank you. Oh, not you. But yeah, that's it. That's the whole paper. Encoding human behavior information design for deep learning. Thank you.
Thanks, Aaryan. Interesting paper, right? I don't know how you deal with this, right? Like we want like some outcome, but also how that works, right? How that really works, right? Because sometimes we are only focused on the labels, I think, right? I don't know. I think it's interesting, right? Any comments for Aaryan here for the paper?
Yeah, I thought it was really interesting using data-driven, like the second neural network to approximate the human behavior, because it seems to me that the behavior is very unstable based on how much information the user has. So if at each, like say model iteration, like our policy iteration, not epochs, like a whole deployment of the model, we can update the approximation that we had from the user actions. Seems like we can avoid like behavior drift and react more properly. So let's say we launched a new product and then our customers start behaving differently. Then I think this model will behave better than like just a Bayesian assumption, something like that. So I think this approach is one of those seem to me to be one of the strengths of how to decide a policy.
Yeah, and the thing is that I was thinking about using for CloudWalk customers, right? But we cannot incorporate this because they say that, okay, if you utilize sender utility more, right? You try to optimize sender utility. You want to destroy the receiver utility. You want to hurt the receiver. And receiver, it could be customers. That would be bad. So in that case, I was thinking Bayesian could be good, right? So we'll assume customer will take the rational decision. But I don't know.
Yeah.
Some things
Yeah.
fail in our case.
The comment about like destroying receiver utility seems more about like how we need to take precautions when choosing what we are optimizing. So if we are optimizing for profit, maybe this will hurt because it will be like a I forgot the word.
So
like maximizing greedy approach. Seems like this would be a greedy optimization, and then in the long term could be bad for us because it will destroy the receiver utility if we choose like profit. But if we choose other more like let's say conservative metrics, then maybe it can be useful. I don't know. I think we should think more about this problem.
Yeah. It could be like this, like how we define utility, right? They say that, okay, sender utility, receiver utility. But if both could be like a little bit related to each other, like sender utility is also like designed good for receiver, right?
Yeah.
So it could work in that way.
And also thinking about like a little bit about game theory. We have like decisions of the receiver and decisions of the sender. There is like this equilibrium where neither of them changes their behavior because they are on a like Nash equilibrium. So maybe like being too good at the sender policy will lead the receiver to be like a constant decision maker as well, won't change the behavior because they seem like they don't have a choice more because we like dominate with all possibilities. So maybe like being too good, as you said, like being too good, like limits how the user will actually behave because we like constrained the user with all information about all choices possible. So yeah, maybe thinking about like the both strategies combined can be a dangerous approach.
Yeah. I was thinking about implementing for frauds. Still confused how we should define sender utility or like. Yeah, go on.
I also think I was thinking of another possible use case, maybe loans and the behavior being not paying the loan. So the utility for them is not paying. So that would also be interesting, right?
Yeah, loans.
Makes sense.
Yeah.
Sometimes we could think about like the policy like being almost like a deterrent. Like if you pay your loan, nothing happens. If you don't pay, we bomb your house. Then you are more inclined to pay, right? So maybe like this is extreme case, but this is a way that the sender can control exactly how the receiver behaves just based on the utility of each choice.
Yeah, it could be like this, right? What sender and receiver utility is how much he will pay the loan, right? Paying loan will, I don't know, hurt the receiver. For some receiver, it will hurt to pay the loan, but we want them to hurt to get the money back, right? So sender, this could be very interesting in this case.
Yeah, we need to choose an approach where the receiver understands that not paying is worse than paying.
Yeah, not paying is worse than paying.
Yeah. Yeah, like bombing the house is like an extreme approach, but the receiver will understand that must pay. It's like a shark loan, right? If you don't pay, you cut your hand.
Yeah, I was thinking about this, right? This information policy could be probabilities from model. I don't know. Like, okay, if the merchant is fraudster or not in the end. But yeah, like this prior distribution could be our prediction from our main models. Then we define a sender utility, receiver utility. That is the main question, how we design then. And then we can have information policy. And then we can say, okay, yeah, it could be fraud, it could not be fraud or something like that. Well, I would say that, I don't know. So trying to think how makes sense. But yeah, it will be interesting to test on code. But yeah, no, any other questions?